Hi, well, I'm Natalia from the University of Glasgow. I work in the release project, and this is a European project, and we have 8 partners working together. These are 3 industrial partners and 5 academics. So the point of the talk is just to give an idea of what we do in the release project, and particular in WP3, it's work package 3, where we work with language level. And the work that I will talk today about is mainly done at Glasgow University and University of Kent in the UK. So I'll give a brief overview of the release project, the problems with the distributed Erlang, our design of scalable distributed Erlang, then a bit about operational semantics if I get time, and about our future plans. So the aim of the release project is to scale the radical actor concurrency rated paradigm to build reliable general purpose software. And we want to scale it to 10 to 5 cores. So the first question that comes is, but Erlang already scales? Well, yes, it does, but at the time when we started the project, that was 2011, we had few aspects, something like VM aspects. So it's about synchronization of on internal data structures. And then this is language aspects, so maintaining a fully connected network and having explicit placement there. And then another thing is tool support. So why we picked Erlang for our project and distributed Erlang in particular? Well, first of all, it's of course reliability. If something fails, then we pick it up and restart it again. And another thing is scalability. So this is a benchmark of Basho bench. We started with 20 nodes. Then within 20 seconds, we just we killed 9 nodes. And then we get into stable state, and then we restarted those 9 nodes. So the scalability really works, and it's really nice. But what we want is that not only hundreds of cores working together, but thousands of cores. So distributed Erlang, if you look at the picture, so the blue ones are hosts. Then we have yellow nodes, and these rectangles over here cores. And then we have processes. And we have transitive connections between nodes, which means that all nodes are interconnected with each other. And 2 main aspects of distributed Erlang is about having those transitive connections, which means if we connect 1 extra node, it immediately becomes connected to all other nodes. And another thing is explicit placement. So if we want to spawn a process to another node, we need to explicitly say which node in particular. And so the distributed Erlang scalability limitations. Well, we thought about few of them, and that's the reason we work in the project. So the first one is about global operations. First, of course, is using global module. And this is a picture that it shows the number of cores, number of nodes, and this is a number, this is a throughput. And then we increase the percentage of global operations. And the largest percent is 0.%. And the smallest, so the less global operations we have, the better we scale. And it's not only about the global module, because you can say, well, not that many actual applications use global operations. But RPC call is also another example when we use global operations. Another thing I want to stress here is, here I will talk about nodes. So how many, and by node I mean an Erlang VM. So how many Erlang VMs can work together? And here I'm not talking about size of one VM. That was talked by Kostis Sagonas, that his part in the release project to scale 1 VM, so how many cores of 1 VM can work. Our aim is to make as many VMs working together as we can. And another problem is single process bottleneck, something like Rex process in RPCs. So this is a picture of Riak This is a benchmark we ran. So we have from 10 to 100 nodes. And then, so it scales pretty well until we come to 60 nodes. And this is React version 1 point, I think. So it's pretty, not the newest version, because we worked with Basha and discovered the same problem together with this Rex problem. They solved it in the next version, but we didn't do benchmarks with that version anymore. And another thing that we think causes a problem is all-to-all connections. We don't have evidence for that yet because we haven't run that large benchmarks yet, but we think it will come. The types of benchmarks that we use. First one is DE bench, and this is an artificial example. And it's nice to use it. It's simple. We understand it. But it's not really very related to the real world. Another benchmark that we ran was REAG, and that's nice. It's large, it's real world, but it's so complicated, it's so hard to understand immediately what's happening there. So we went something in between, and this is Orbit. So why Orbit? First of all, it's DHT, so it's similar to REAG. Another thing is it uses peer-to-peer techniques. And the last thing, it's quite small, so we can understand what's happening there. And it's sort of close to the real world. So Orbit. Just a few words how it works. We have a master node, and we have worker nodes. And we start process on the master node, and it generates a list of processes. So where we spawn the next process depends on the hash value of that process. The hash table is distributed between all nodes. So we generate an element, we take a hash, and this hash defines to which to which node we actually are going to spawn the process. So if we have just one node, then we just spawn it just spawn it, and that's it. And then by the value define the hash value of the table. If we have a distributed Erlang, then we need to define a node here. But that's actually the difference between non-distributed Erlang and distributed one. So now I will talk about scalable distributed Erlang. And so before I will explain what it is, I'd like to say a few words how we designed it, how we came up with the idea, why it looks the way it looks. So the first one is the design principles. And the first, so general principles are about working on Erlang level as far as possible. Then we wanted to preserve the Erlang philosophy, which means and programming idioms. And then we wanted to make as minimal language changes as possible, because language is nice. It's simple. It has its follows. So we didn't want to introduce something foreign that programmers later will just reject and say, no, it's not our Erlang. We don't want to use it. And then about reliable scalability design principles. So it's about avoiding global sharing. It's about introducing abstract notion of communication architecture and keeping Erlang reliability model. When we started, we looked at the following few things. So the first one is about typical hardware architecture. So what we think will be the architecture that we'll use as the Erlang. Another one is anticipated failures. So what's going to fail while running an application, and what we need to scale. So we thought that first of all, we need to scale persistent storage, and we think that React and Cassandra can do that for us. Another one is in-memory, so these are ads tables, and currently our partners in the release project in Uppsala University and Ericsson work on that to scale ads tables. And our beat is about computation, how to scale a computation. So the first one is the target platforms. So we target commodity hardware. So it's general purpose, it's a standard hardware and operating system, and not specialized. So we thought something like this. So we have clouds, we have clusters, within clusters we have hosts, something like 100 hosts per cluster. And then we have these modules, something like that have a shared memory. And then we have those modules, around 32, 64 cores sharing a memory as well. So it's about a NUM architecture. And SD Erlang and its scaling computation. So SD Erlang is a conservative extension of distributed Erlang. And it consists of two parts. The first part is network scalability, and the second part is semi-explicit placement. So the problem with it is we don't believe that all-to-all connections scale. So we wanted to change that. And another thing is semi-explicit placement. So, okay, if we have 100 of nodes, or we have something like a structure, how we name nodes. But in general, it's just impossible to know the whole structure, to spawn processes to particular nodes everywhere. So that's another thing. So the first one is network scalability. And here we have two types of nodes. We call them free nodes and S-group nodes. So free nodes, these are nodes from distributed Erlang. They have the same rules. They connect, they have transitive connections, and they have the common namespace. And S-group nodes is the node that belong to S-group. I'll explain in a minute what I mean by that. And nodes in S-group have transitive connections within nodes of the same S-group and non-transitive connections with other nodes. So the first three pictures is about distributed Erlang. So for example, we have two groups of nodes, and then we connect node 3 and node 4. And what we get is a fully connected network. That's what I mean by transitive connections. And if we have S-groups, it means we have one S-group, another S-group, we connect nodes, and those nodes have non-transitive connection. So they connect, but first of all, they don't share their connections. And the second thing, if we register a name using global, for example, then those nodes will not share that information. And here, a bit more about the type of nodes we have and types of connections. So the black nodes are normal nodes. What I mean by normal nodes, they're not hidden. And the gray nodes are hidden nodes. So when hidden nodes connect, they have non-transitive connections. They don't share connections. And and here we have S-groups. And the feature of nodes in S-group, they can belong to multiple S-groups. That is, if you look at S-groups, you may say that, well, that's quite similar to global groups. Well, the difference between global groups is that nodes can belong to, in global groups, nodes can belong only to one global group. And S-groups can belong to multiple groups. Right. So the question is, why S-groups? So there are a few reasons. So we wanted to preserve distributed Erlang philosophy, and that is any node can connect to any other node. We didn't want to introduce restrictions there. Then we wanted that adding and removing nodes from S-group should be pretty simple. And a node should belong to multiple S-groups. And again, the mechanism, we didn't want to overwork over them. So we considered a few approaches. The first one was according to hash value. That's a pretty popular idea, and we thought about it. But then removing and adding nodes to groups become pretty complicated and brings more headache than it brings positive things. Then we thought about hierarchical architecture. But here, it means that nodes, we can't connect actually any node to any other node, because if it's hierarchical, it means that nodes can be connected to only within their group, and they can be connected to the parent and to child nodes, but we can't do interconnections over there. So we just decided to do overlapping and see what will happen. So as groups, we can start them at launch. So we can define a configuration file and say, here is our configuration, and please have those S groups. Or we can start them dynamically using one new S group 0, Right. No, it's new as group 1 and new as group 2. I'm sorry. These are those two functions. So in the first one, we define only a list of nodes, and then the name of the as group is generated automatically. And in the second one, we also define the name of as group. We also can delete as group, add nodes to as groups, and remove nodes from as groups. And there are additional functions, of course. So a list of own nodes that's about as group information. Then we can register and register names in as groups, searching and sending messages. So we did run some benchmarks using DE-bench here, and we ran from 10 to 100 nodes. And the experiments showed, yes, having even 0.01% of global operations does improve scalability. So SD Erlang scales much better than distributed Erlang. And now looking at Orbit again. So we have this Orbit, and how we want to refactor a program in distributed Erlang to SD Erlang. And that is introducing levels, actually. So we have the same master, but now master is connected not to worker nodes directly, but to submasters. And then submasters actually connect to worker nodes. I will explain a bit how each bit works. So distributed Erlang, we have master, worker, table, credit. And here we add a few more modules. There's submaster and grouping. And then for master, the difference is that now it spawns not worker processes, but it will spawn submaster processes. So master node, it's no longer has direct connection or communicates with worker nodes, but rather it communicates only with submasters. And workers, now, for example, when they want this worker want to send a process to this worker, it first check. So we do not one hashing, but two hashes. So the first hash we check whether the worker that we want to send the process is in the same as group. If it's in the same as group, then we just directly send the message. If it's not, then the message goes to submaster, to another submaster, and then to the worker process. And submasters, so they will initiate submaster and gateway processes, start worker processes, and do so the submasters, they become something between. They take roles from worker processes and worker nodes and take the work from masters. So they become something intermediate that connects masters and workers. And grouping. So now we need to create a master group and submaster groups. That's about grouping. These are initial experiments that we ran on up to 160 nodes, and that is about 1,200 cores. If you see the distributed Erlang and scalable distributed Erlang. So scalable distributed Erlang performs a little bit better, but the difference is pretty small. These are initial experiments, so don't be too scared by them. But important thing I want you to notice is this flick that happens around 30 nodes. So for this particular benchmark, the difference is small, but it's important that this flick happens and then the distributed Erlang actually performs better. Maybe this is...
What's the vertical axis?
Oh, I'm sorry. Oh, I can see that myself. Right. It's runtime. Runtime, I'm sorry.
Right.
Yes, so it's runtime and nodes. And then we look at the speed up. So it's this is speed up, and those are number of nodes. So again, distributed. So we have this flick here, and scalable distributed Erlang performs a little bit better. But again, these are initial experiments just to see, because we did the work, and so the question is, does it actually work? Does it help SD Erlang? So it shows that it does. Right, so another part of scalable distributed Erlang is semi-explicit placement. So semi-explicit placement is about processes, placing processes, where we place those processes. So for example, we have a processes that communicate very often with each other. So it means that we want to place them close to each other. Another thing is that probably we have a process that will run for a while, and it means that probably we don't want to run it locally, but we would rather to send it somewhere, to some cloud or somewhere. So we want to make it not by hands, but some sort of automatically sending into different groups. And here we can imagine actually the structure of our system, something like a tree, right? So, for example, these are racks, and those are clusters, and this is the cloud. And what we do is we work with a metric system, which is close to, I forgot its name, it's over here. Yes, it's right, Euclidean space. So what it means, I'll get back to this one. So it means that actually we can define the distance, and here we go from the root. And this research is based on the research done at Glasgow University by some of the researchers. They worked with Haskell, and so we decided to take the ideas and try to implement it in a bit different aspect. So what it means is that we look from the root, from the top, we look at how many those links, branches, actually, to nodes have in common. So B and C have 2. It means that their distance is 1/4. And B and G, for example, that they have only 1. It means the difference distance is 1/2. And when it's no common links, then it means it's 1. So the larger this parameter, it means the further nodes are from each other, and from this we can define how far nodes located from each other. And here we can look at the radius. So we can, when we define where actually we want to spawn the process, we can just look at this radius and see how far or close we want to spawn. And here we can think about something very specific, right? We can think about 1/4 or 1/8. But on the other hand, we can do it more user-friendly and using some nearby, very close, far away. So this kind of parameters. And this is a work in progress. Another thing that we can use is using attributes and as groups. So first of all, how we can group as groups, or how we can group nodes in as groups. The first thing that can be, of course, that's locality. Nodes are close to each other, we put them in as groups. Another thing can be, well, probably those nodes have the same hardware, or they have the same software, and so we can group nodes in that way. Or we can group them according to locality, but then give them attributes. And these attributes can be, maybe they have some software, maybe they have some parameter there, maybe just, I don't know, somebody's friend's computers or something. So just using all those attributes will also help. So we came up with a choose nodes function, and it's a list of parameters. And those parameters that can be as group, that can be an attribute, or that can be a distance. For example, close, far away, and so on. Another thing that we are working is operational semantics. So for SD Erlang, we work on the semantics. Why we need it? Well, we need to be sure that what we actually work with and what we write is correct. So we want to check it. And for this, we came up with 9 functions that change their state and 6 functions that don't change their state. So so initially, a node has some sort of a state, and the functions that don't change their state, so the state doesn't change, but still we return some result. So for example, where is the name or register name, and so on. So the state is actually about as groups, a set of as groups, a set of free groups, By a free group, we mean a set of normal nodes interconnected to each other. And then a set of free hidden groups. And free hidden groups, it's actually, every hidden node is a free hidden group, because a group we define as having its own namespace and consists of nodes with which it has transitive connections. And of course, hidden nodes, they have their own namespace, they don't share it, and they don't have transitive connections with other nodes. So the property here is that every node in SD Erlang is a member of one of these groups. So we can say that nodes over here, each node from over there belongs only to one of those. And here we can derive all sorts of properties. So the semantics looks like we have a state in the beginning, we have a command, and we have a node on which we implement this command. And then we have a new state, and we return a value. And this is just a very, very simple example, the simplest that we have. I don't want to overload you with this. So we have an initial state. We have groups, free hidden groups, and nodes. And we want to register a name in S group that has a name, that has a PID, or node NI. And so we check. So the first thing is that the node should belong to the S group. And if the node belongs to the S groups, and the name is not registered, and the PID is not registered, then we register the name. Otherwise, nothing changes, and that's it. So, and we verified that, and for validation, we used Quick. This is a quick check, sorry, from company Quick. The way we did it is that, so we have an S group command, and we go into two different directions. So we take operational semantics, we take a state, we apply the semantics that we used, and we get a new state. And then we actually run the actual command. And then we get these two states, and we check whether they fit, whether they are the same. And if they're the same, that's fine. The function works fine. If not, that's something wrong. And actually, we identified a few problems with our functions this way. That was really useful. So just to give an idea what's happening there, so the precondition, for example, for creating a new S group is that set of nodes shouldn't be empty. So this is the precondition that we check in the beginning. And then we have a post condition. So those two were checked. Each of them went through their way. And then in the end, we check those, we get abstract states, and we checked them with the real state. So abstract results, we compare with the actual result, and abstract state with an actual state. Right, so now about future work. In the release, we got 3.5 years, and we are 2.5 years just now. So we get one another year to work on. So the semi-explicit placement, that's really interesting word that we are very excited about. And here, so currently what I showed is actually we have everything written in configuration file. And of course, we want to make it automatic. So that's one thing to do that. And we also want to look at robustness. So adjusting parameters and looking at the failures. Another work is continue to work on the SD Erlang semantics. So probably look at other function, look what we can do there, check the existing functions. Another very interesting work that involves almost all partners in the release project is actually running SimDiaska on a BlueGene supercomputer with approximately 65,000 cores. That's going to be an exciting work with a lot of large VMs and a lot of VMs actually working together. So quite a lot of work just now happening around SimDiaska simulation engine that was developed at EDF, that's in France. We also would like, we want to work on it as the Erlang to become a standard Erlang, but for that, of course, we need to run benchmarks to convince the community that it's worth adding it as a standard thing. And of course, in the methodology. So the first thing in the methodology is about portability. So running the same application on different machine, and of course here we look at choose node function as our main thing. So just having parameters, extracting those parameters from the system and adjusting them, helping the system to decide where exactly to spawn those processes just from some small hints. And scalability principles. So these scalability principles are first about, of course, Erlang applications. So we developed a library and we continue developing it, but for developers, I suppose, it's really important how to use this library, so what to do with it, how to structure the program. So that's another thing we look at. And then from the research point of view, it's also very interesting to know what sort of, what things that we learned from Erlang can be applicable to other languages, how they can use the same techniques to improve scalability of all sorts of languages. Yes?
The simulation you referred to with 65,000 cores, how many nodes?
Right. It's a blue gene. I think Kostis is not here. I asked him today, but my focus was about how many cores there. 64 something.
With Erlang, you care a lot about the number of nodes.
Right, yes. So I'll tell you, it's I think either 16 or 64 cores per node. Sorry? 32, 64, right? Yes. Okay. So it's something like that. But yes, here, so I mean, VM, it will take something like 62, so it depends, 30, so assume it's 32, but we can actually put more VMs, right, on one host. So we can have actually more VMs than just that number. Right, and scalability principles. These are some sources that we worked on. So release project, just some general information. We do public deliverables there, so if you're interested, do have a look. Then in GitHub, SD Erlang, of course, DE Bench and Orbit. These are benchmarks that we worked on. Percept2 is a tool that Kent University works on. BenchErl, we also use, that was developed at Uppsala University and ICCU in Greece. And SimDiaska, simulation engine, that is the work of EDF. And that's it. Thank you, and your feedback will be very much appreciated.
We have time for questions.
Yes.
One of you considered it a master and then a submaster. If
Yes.
that submaster dies, is there an election process within the pool to re-elect a new one?
Right. Well, just now we don't provide it from the language perspective. We rather leave it just now to programmers to decide. Because, for example, that submaster, you can think of it like creating more submasters, for example. So you can elect this from the workers, for example. Or that can be, that dies, and you may want, depending on your application, you may actually want to kill all your other workers and restart everything from scratch. So just now we don't focus on it that much, but probably that will be one of the direction when we look at the methodology and portability. So what sort of patterns we actually can, because one of the patterns is grouping, because everybody can do grouping themselves. But actually, when we ran those benchmarks, we realized that we can do grouping as just a library for just, because it's just reusable, use it all the time. So probably that can be a pattern as well. Yes, please.
So when one worker in a particular S group wants to talk to or wants to send a message to another worker in a
Yes.
different S group,
Yes.
how does that worker in the first S group know where the message needs to go? Like you
Right.
mentioned about hashing.
Yes. So, I mean, you can build your application in such a way that submasters will know. So the node will be aware of its surrounding, so it's directly connected. And then you do the hashing, and you see that it's not in your network, so you just send to submaster, and then submaster decides where to go. Another thing is nodes can actually be directly connected. It just depends on the application. So the difference is that just, if you have transitive connection, oops, I went to the wrong direction. If you have transitive connections, it means that nodes are not going to share this connection. So, for example, if you connect this to nodes, it means if you something registered here, it means that first of all, these two nodes, they will not share the connections, so they will not become fully connected. And another thing, if something is registered here, doesn't mean that it will start replicating on this network. So, but it depends on the application what we can do there. Yes, please.
Did you find that there was an ideal S-group size?
Right. Yes. We looked at it, and I think there was. We looked at it on for orbit example, and I think that was something like something like 20 nodes, I suppose. But I think it's very application dependent, and it depends on how many global operations you're actually using. Because something like React is good 60 nodes. So you can grow your network up to 60 nodes, and then it's better just start. But if you, in DE bench, I think, if you don't use global operations at all, then you can have a network of 300 nodes. And your fully connected network will work just perfectly. So I suppose it's very much application dependent. Yes, please.
Are you worried that, on the supercomputer it's not an issue,
Yes.
but on the internet, if this S-group architecture means that edges between fully connected subcomponents become very, very high stakes, do you think that's going to have serious robustness problems in the long run, or do other aspects of the Erlang architecture make up for that? It seems like if you lose
Yes.
that connection, nodes can't discover each other until the subs are back up and running. Right?
Yes. Yes, but I think it's very much about reliability, right? So, if yes, you mean in the distributed Erlang, if you just lose one node and then it comes up, then it's enough to connect to just one of those nodes, and it will be enough. But on the other hand, yes, I think it's very much about reliability. So instead of having just one submaster, you will need to have two submasters or something like that. Think about mechanisms how to ensure that the network is not lost. Yes, please.
So in one of your earlier slides, you mentioned the issues that you have with Rex being a single serialization point. Did you have issues with your masters and your subclusters there becoming serialization point for distributing the rest of the work around? And I was just interested if the release project has looked at anything like having some sort of round-robin thing based off naming, so that you can have a pool of processes that would respond rather than a single process, and if you had any scaling issues there?
Right, that's a very interesting point. I'm afraid we haven't reached that point yet. Probably SimDask, I suppose, is the one that will show us quite a lot of interesting, problems arising there. Because currently with Orbit, it's quite small, and we didn't have many problems getting there. So, but that's interesting, really.
And the other question I was interested in was why were you measuring the distance to the root node of the network rather than just a simple hop? What was the benefit of sending the metric out like that?
Because this matrix is very much about communication time.
So why not use hops then? Why use? It looked like you were measuring
Yes.
the 2 to the negative number of shared connections. to
Yes.
the highest root node, whereas you may have a real network that's not actually a hierarchy like that. You may have mesh networks. There may be multiple paths in the network
Yes.
to get to nodes. So I was just interested why you picked that rather than doing hops.
Right. Well, I suppose it's because we can have different types of connections, right? We can have something that, for example, for example, looking at 2 hops, for example, if you don't have hops, it's pretty easy. But suppose we have 1 hop, and we have 2 hops. And if through 1 hop it's very busy, and 2 hops are not, then it means that through 2 hops it will be much quicker than through this 1 hop, right? So it's not actually very much about how many hops we do, but how much time it takes. So I suppose our main concern is about communication time, because it's one of the bottlenecks rather than just counting hops. Another thing is that sometimes when you route things, right, the packets, they can go through different routes, right, to the same point. So I suppose the main thing that we want is that to measure the communication, actually, not exact direction. Yes, we're interested more in time, how long it takes, rather than which exactly path it takes, I suppose.
So, yeah, I'm sorry.
No, I just didn't hear you.
You're passing messages between intermediate broker nodes between your different S groups or G groups. And so in such a case, that's why you might have to take the extra distance into account, because you have to proxy through various groups.
Yes. Yes, that's one of them. Yes, please.
I think what you're doing is actually building a small internet inside the whole nodes. And are you going to, did you try to implement, change some lower layer protocol of the Erlang VM using UDP or somewhat more stateless protocols or something like that in this simulation, or whatever you try to experiment in this research?
I didn't understand the point about.
From your presentation, I thought you were doing it on the application layer on the TCP. Is that right?
Yeah. Yes.
Okay, so I'm not saying that is ineffective. That is ineffective in some, at least on some level. But if you are doing this kind of complexity, especially on 10,000 or more nodes, you are trying to build an internet service provider inside the all the nodes. I'm just using a kind of analogy, so that you have to implement different kinds of routing strategy, such as Brown fold algorithm or more mesh algorithm on a different part of the internet and with different cost structures.
Right.
So it's not something you can mathematically draw from my personal experience and lots of empirical reports on the internet operation.
Yes.
It's not something that you mathematically draw or converge into something,
Yeah.
some steady solution.
Yes. Well, I'm not very agree with you in terms of building internet, because I mean, BlueGen is just this box. It's not internet. It's just this tiny bit of.
I know. If the link characteristics is quite uniform and homogenized,
Yes.
you can assume like that. But what you're going to do is a very much highly complex node connections. It's not something like React or 100 nodes or something like that. If you're going to expand all these to 60,000 or 100,000 nodes, you have to think totally different. That's my. I only want to like to give you a sort of
Yes. Yes.
operation standard on it.
Yes. Well, I think I want to talk to you more about it.
Yep.
Yeah. Thank you. More questions?
One
Yes,
last
please.
question for you. If you're using hashing to determine where this thing is located, are there concerns in a heavily loaded system about things hashing the same and creating hotspots throughout the?
Right. Well, I think hashing in this case was just it was easy to implement. I'm not sure that hashing is actually something standard that probably many applications are going to use. Another thing is that I think it's a bit hard to answer your question because we didn't look at too many applications. But that's an interesting point. Yes, thank you. Yes, please.
You said since individual nodes can be in multiple S groups, I can certainly imagine various developers trying all sorts of interesting topologies to see what they can do.
Yes.
Does the performance go down linearly with the number of S groups a node is in? Is it worse than linear? Like, can you put one node in 1,000 S groups and have it still be reasonably performant?
I suppose it depends on what you are going to do with that. If you're going to register names all the time there globally, I'm afraid that will be pretty bad.
Well, if you're not using global, but just, for instance, wanting to be have that the fully meshed network within the single S group, and you're in a lot of S groups, I can imagine that at almost the VM level it might be problematic.
Um,
Wouldn't you just degrade fully connected out? Wouldn't you just degrade fully connected out? The more S groups you're in, the more connections you can have between nodes, and you're defeating the purpose of.
Yeah.
I suppose yes. I suppose it depends. Thank you. I suppose it depends on also how many connections a node can hold, right? So probably the degradation can come from there. But other than that, it will take time for you to create those S groups, 1,000 of them. Synchronization shouldn't be a problem if you don't register anything. So it's only about actually keeping connection. You're not updating anything there. If you don't add nodes, so, I mean, if you just hold it, I don't think it's going to be a problem. It's like having just direct connections like with hidden nodes, and that's it. More questions? No, well, thank you.